Hi, today I would like to talk about the basic searching technique part 2 that will focus on the heuristic technique. So what is a constructive heuristic? So the constructive heuristic work by constructing a solution step by step, evaluating the solution for feasibility and the value for the objective function. So it is a greedy or myopic. The constructive heuristic is a greedy approach or myopic approach that is narrow-minded. They take the best thing next without regard for the rest of the solution. That is, they think they only take the solution which they think that is best at that time. So for example, take the nearest city next for the TSP. So this is like nearest insertion first, for example. So example, the traveling salesman problem. Salesman need to visit n cities, including his own city. He wished to determine a minimum length or minimum time or minimum cost tour that visit each city exactly once. So except that it begin and end his home city. So travelers need to visit n cities. Know the distance between each pair of cities. Want to know the shortest road that visit all the cities once. So for example, if n equals to 80 cities, it will take millions of days to solve exhaustively. That is 80 factorial. Traveling salesman problem. Let's say the distance between city 1 and 2 is 3, 1 and 3 is 4, 1 and 5 is 2, 1 and 4 is 1. Similarly with other city, 2 and 5, for example, is 3. So 3 can be 3 kilometers, 3 hours, or whatever it is. So this is the cost of traveling among the cities. So how might we construct initial tour for TSP problem? So there are some heuristic or some constructive heuristic to construct an initial tour for the TSP. So one is nearest neighbor heuristic, second is furthest insertion, random constructive. So let's have a look on the nearest neighbor constructive heuristic. So begin with any cities, let's say X cities. Select among all currently unvisited cities the one which is closest to X. Call this city XY and add the road XY to the tour. If all cities are visited, stop. Otherwise, let X equals to Y be the most recently added city and go to step 2. So we repeat step 2 until all the cities has been visited. So this illustration of the nearest neighbor heuristic. So have a look. Let's say we start with city 1, and then the nearest city to the city 1 is 4 because the distance is 1. So 4 now, what is the nearest city to city 4? So have a look. 4 to 2 is 4. 4 to 3 is 5. 4 to 5 is 3. So which one is the nearest? So have a look, here is 4 to 5. So the next city to travel is from 4 to 5. And now 5, look at the closest city to city 5. So 5 to 1, 1 is the home city, so we do not consider that road. Then 5 to 2 is 3. 5 to 4 already visited. So now only have 5 to 2 or 5 to 3 is 2. So we consider 5 to city 3 because the distance is 2. Now, what are the cities that has not visited yet? What are the cities that have not been visited yet? So there's city 2, I think city 2 only left. So we go to city 2. So next, for all cities has been visited, now we back to city 1. So the total distance is, we compute from city 1 to city 4, that is 1. 4 to 5 is 3, and add up all the distance, so the total distance is 11. So this is another illustration of the nearest neighbor heuristic. So we start with different city. Let's say start with city 3. We start with city 3 as the home city. So see, from 3 we go to 2 because this is the nearest distance, and then 5, 1, 4 until 3. So the total distance is 13. So let's have a look on best first search. So best first search combine the advantage of breadth first search and depth first search. So DFS, depth first search, follow a single path. You don't need to generate all the completing paths. So breadth first search doesn't get caught in loops or dead end paths. So best first search explore the most promising paths seen so far. So while goal not reached, generate all potential successor state and add to a list of state. So pick the best state in the list and go to it. So this is best first search. So similar to steepest ascent, we will study about steepest ascent later, but don't throw away states that are not chosen. So let's see A-star algorithm. The A-star algorithm uses a modified evaluation function and best first search algorithm. So A-star minimizes the total pass cost. Under the right condition, A-star provides the cheapest cost solution to optimal solution. So under the right condition, A-star provides the cheapest cost solution in the optimal time. So the evaluation function f is an estimate of the value of a node x given by fx equals to gx plus h prime x. Gx is the cost to get from the start state to state x, while h prime x is the estimated cost to get from state x to the goal state. This is the heuristic. So we will have a look on the example later. So modified state evaluation. Value of each state is a combination of the cost of path to the state, estimated cost of reaching a goal from the state. So the idea is to use the path to a state to determine partially the rank of the state when compared to other states. So this doesn't make sense for DFS or BFS, but it's useful for the best first search. Why we need modified evaluation? Consider a best first search that generates the same state many times. Which of the paths leading to the state is the best? Recall that often the path to a goal is the answer. So in A-star algorithm, best first search with the modified evaluation function, h prime x is an estimate of the number of steps from state x to the goal state. So loops are avoided. We don't expand the same state twice. So information about the path to the goal state is retained. So this is the A-star algorithm. First, we create a priority queue of search nodes. Initially, the start state priority is determined by the function f. So while queue not empty and goal not found, get the best state x from the queue. If x is not a goal state, generate all the possible children of x. and save past information with each node. Apply F to each new node and add to the queue. So remove duplicate from queue using F to pick the best. You will get more clear when we go to the example later. This example of the maze. So if we look at this example, what is in front of us might be the best for now. So if you follow like this, so you might have to go like this. So we take long step. If you go like this, you will circle here. But if you go like this way, you will get the goal more faster. So this is heuristic. Which step to go? Either this way, or you can go up like this. So we need an estimation. What is the best step by looking at the goal. So ISTART optimality and completeness. If the heuristic function h prime is acceptable, the algorithm will find the optimal shortest path to the solution in the minimum number of steps possible. That is, no optimal algorithm can do better than the same heuristic. An admissible heuristic is one that never overestimates the cost of getting from a state to the goal state. It's pessimistic. Let's see the example of A-star algorithm. So these are the cities in Romania, and these are the distance between cities. So for example, the distance between Arad to Bucharest is 366, from Arad to Ifori is 161, and so forth. So the task is, what is the shortest distance to travel from Arad to Bucharest? So Arad to Bucharest, what is the optimum traveling distance? So now we start with Arad. The open list, we have only Arad. We start with our initial solution, initial state, that is Arad. We make a node and add it to the open list. Since it's the only thing on the open list, so we expand the node. Think of the open list as a priority queue that sort the node inside of it according to their function GH plus SS4 and Zerin. So the distance between Arad and Sibiu is 140. The distance between Arad to Timisoara is 118. The distance between Arad and Zerin is 75. So what is 253? 253 is the estimated distance between Sibiu and our goals, the cities, that is Bucharest. So this is a straight line distance between Sibiu and Bucharest, that is 253. So the total estimation from Arad to Bucharest through Sibiu is 140 plus 253, that is 393. Similarly, the distance to travel from Arad to Timisoara, then straight line to Bucharest, is 447 and Zerin is 449. So based on this estimated distance, we sort the list. So the top in the list is Sibiu, that is 393 distance. So we add the 3 node and found the open list. So now, when we expand Sibiu, we run into Arad again. So, but we have already expanded this nodes once, so we don't add to the open list again. So we remove Arad from the list. So now, have a look. From Sibiu, we have 4 cities connected. We have Arad, we have Figueres, we have Oradea, then we have the Rimrichu Visia. So these are the distance Arad to Sibiu. From Arad to Sibiu is 140. From Sibiu to Rimrichu Visia is 80. So we have 140 plus 80. So we have 140 plus 80, we have 220. The total distance from Arad to Sibiu to Rimrichu. So we have 220, and 153 is the distance, the estimated distance between from Rimrichu Visia to the Bucharest. So the total 220 plus 193 we get 413. Similarly for other cities, similar calculation. So when we sort the total distance, we found out that the distance to travel from Arad, Sibiu, Rimrichu Visia to the Bucharest is the shortest path at this time. So that is 413. The rest is more than 413. So we select Rimrichu to be open for the next cities to be visited. Okay. When we expand Rimrichu Visia, we run into the Sibiu again because Rimrichu Visia is connected to Sibiu. Since we already visited Sibiu, so we remove this from the open list. We remove Sibiu from the open list. So now let's have a look. We have 3 cities connected to Rimrichu, that is Craiova, Pitești and Sibiu. Since Sibiu is already visited, so we remove from the list. So we still have an open list where we have Figueres, we have Pitești, we have Craiova, we have Oradea, we have Timișoara, we have Zrin. All these are still in the open list. So among these, the top in the list, that is the shortest in the list, is 415, that is Figueres. So this is the shortest. Previously we visit Arad, Sibiu, Rimrichu. So when we open the list and we sort all the other cities that we have, the path that we have traveled, so we found out that Figueres is the shortest path. So this we move up again here. So Figueres will be the next node. We should expand it at the top of the sorted open list. So now have a look. When we expand Figueres, we found Sibiu again. So we open Figueres, we found Sibiu again because Sibiu is connected to Figueres too. So we don't add it to the open list. So we remove Sibiu. We also find Bucharest. But we are not done yet because Bucharest is not at the top of the list. So the algorithm doesn't end until we expand the go node. It has to be at the top of the open list. So now we open the next. From here, we found that Pitești is the shortest cities to travel. Found that the next city to be visited is Pitești. So we need to open Pitești for next node. When we look at here, Pitești, when we visit through Pitești, we got 417. The rest is more than that. So it looks like Pitești is the next node we should expand. So when we expand Pitești, we found that city Bucharest, that is our goal city or target city to be visited, or last city to be visited. Then we also have Craiova, we have Rimrichu Visia. So among all these, Bucharest is at the top of the list, that is 418 travel. So we just found a better value for Bucharest. So it got higher in the list We also found a worse value for Craiova. We just ignore it. We ran into Remedial again since already been expanded once. We ran into Remedial Visia again since it's already been expanded once. We don't re-add it into the open list. So we remove Remedial Visia. So now Bucharest at the top of the list. So now it looks like Bucharest is at the top of the open list. So this means that we already achieved our goal. So now we expand the node for Bucharest. We are done, and we know the path that we have found is optimal. That is 418 in kilometer. So we have done to travel from Arad to Bucharest. So the goal is achieved. So this is the optimal path to travel from Arad to Bucharest. So now let's have a look on graph. Okay, let us move to graph coloring approach. This is another constructive heuristic that we call graph coloring. So we talk about coloring graph and match chromatic number application of graph coloring. Color a map such that two regions with common border are assigned to different colors. Each map can be represented by a graph. Each region of the map is represented by a vertex. H connect two vertices if the region represented by these vertices have a common border. Let's say, for example, we have Malaysia and Thailand. We are neighboring country. So if we represent this in a graph, so these two cities must be connected. So there must be a and H connect between Malaysia and Thailand, or Malaysia with Singapore. So how to color a graph? A graph has been colored if a color has been assigned to each vertex in such a way that adjacent vertices have different colors. For example, we color this with yellow. So all the nodes connected to these vertices cannot be colored by yellow. So this is connected to the yellow vertices. So we color in brown, for example, light brown. This one connected to yellow, so we color light brown. This one same color with this one. Since they are not connected, they can reuse the same color. Similarly, this one dark brown. So dark brown and brown, they are connected, so we cannot use the same color. Actually, this one is blue. So how many colors we have? We have 1, 2, 3, 4 colors. So the chromatic number of a graph is the smallest number of color which it can be colored. So in this example, the chromatic number is 4. Example, how many colors do we need for this graph? So you count this is the minimum. How many colors do we need for this graph? We have green, dark brown, and blue. So 3 colors. So the chromatic number is 3. Graph coloring application. Map coloring, this is the direct application for map coloring. Countries are vertices, and adjacent countries that share a boundary are connected by H. In real maps, adjacent countries are assigned to different colors. Another example of graph coloring application is timetabling problem. So given a list of courses, and for each course, the list of students who want to register it. The goal is to find a time slot for each course using a few slots as possible. If a student is registered for courses P and Q, and age between P and Q is exists. So the resulting class can be colored with k number of